Hello students, myself Dr. Divya, Assistant Professor at Department of Chemistry, Institute of Aeronautical Engineering. So in this session, we will discuss the numerical problems of EMF of a voltaic cell. So EMF is nothing but electromotive force for that particular cell. So before going to the numerical problems, we will just have a glance and what is the EMF? It is the electromotive force is nothing but the maximum potential difference between these two electrodes, electrode 1 and electrode 2. So the potential difference between these two electrodes of any galvanic or voltaic cell is called as EMF of that particular cell. So in the next slides, we will be seeing notations like this. So this is the cell notation. So in cell notation, we have, for example, zinc is becoming Zn2 plus and copper 2 plus is becoming copper. So wherever there is a change in oxidation state, there is some reaction going on. So the 0 state is converting to +2 state. It means increase in the oxidation state. So this is therefore called as oxidation is taking place and anode. This is the anode. So this is the anode, and wherever there is a decrease in oxidation state, that is +2 ions to 0, that is reduction is taking place and the copper will be depositing on the copper electrode. Copper is depositing on the copper electrode. So this is cathode. This electrode is called cathode. So there are some lines in between these elements. So this is the change in state. This indicates change in state between these two. It is converting from metallic to Zn plus ions and Cu2 plus ions from the copper sulfate. This is the copper sulfate. Cu plus 2 ions from the copper sulfate is converting to copper. So this is a change in the state. That is why there is a slash given, and all the notation wherever there is a single slash, it indicates change in the state, physical state. And there are two double slash present between these two cells. So this double slash indicates the salt bridge. So this is the salt bridge. So what is a salt bridge? Why we really require this salt bridge? To maintain the equilibrium between the ions. So the ions present should be maintained. So if you see in the equation form, all the problems from the electrochemistry will contain the equations like this. So the zinc is converting to Zn2 plus and 2 electrons are liberated. So this is the E, that is the potential of that particular electrode. So single electrode potential. So using these single electrode potentials, we will be calculating the EMF or the electromotive force for that particular cell. So if we see this series, so this is all called as electrochemical series, which is given. So these are the arrangement of different electrode potentials for any element or the metal that is from the that is forming the electrode in that particular cell. So they are arranged in such a way that highest negative values to highest positive values. And this is called as electrochemical series. So if at all the problem is not given with the electrode potential, we have to memorize this electrochemical series and imply the potential given for that particular element. So let us see the examples, like what are the problems that can be solved. So calculate the EMF of a cell for a given half cell reaction. So they have given half cell reactions to us, like zinc is converting to Zn2 plus and 2 electrons. So it is having an electrode potential of minus 0.763 volt, and the copper ions receives these 2 electrons and forms copper. So it is in the 0 state, and it has the potential, electrode potential of plus 0.337 volts. So we have to use this formula, like E cell is equal to E cathode minus E anode. So with this, we have to define what is cathode and anode. There is always like increase in the oxidation state. So oxidation is taking place, and anode, this is the anode, and there is decrease in the oxidation state. So this is the cathode. So this is anode and this is cathode. Now we have known that what are cathodes and anodes in that particular cell. So let us substitute the values. So the cathode value is plus 0.337 volt minus So the anode value is already in the minus. So minus of minus 0.763. On calculation, we get plus 1.1 volt. Whenever there is plus sign, it indicates this reaction is spontaneous. Reaction is spontaneous. Reaction is spontaneous. So the reaction will take place. So these are the examples for EMF of the cell given for the with half cell reactions. Whenever the half cell reactions is given, we have to decide what is anode and what is cathode. So let us look at the other example. Like calculate the EMF of voltaic cell containing iron and copper electrodes. So two cells are connected and one is iron and one is copper. So if we see this aqueous state, it means it is salt dissolved. It is the salt dissolved. Either it can be ferrous sulfate and copper sulfate that is dissolved in water, and they have also given the potentials for that electrodes. So what is the potential for copper? Plus 0.34 volt. For copper, it is plus 0.34 volt. And for anode, for example, iron, it is minus 0.44 volt. So this is a question they have given already. So we have to decide further like how we have to define anode and cathode for that. So here the iron is oxidizing to Fe2 plus ions and 2 electrons are liberated. What is happening here? Oxidation is happening. Increase in oxidation state. Oxidation is happening and anode. Next is a copper. It is taking up these 2 electrons and forming copper 0 state. Reduction in the oxidation state. So this is reduction and it is called cathode. So this is forming cathode. So using the same formula for that we have used for the EMF of the cell, it is E cathode minus E anode. We have to substitute the values that are given in the question. Like for the copper, it plus 0.34, a minus of minus 0.44 volt. So on calculation, we get plus 0.78 volt. Again, it is plus, so it is spontaneous reaction and the reaction is feasible and the reaction is feasible. So whenever there are chemists like working in the electrochemistry field, they keep on calculating this EMF for that particular cells depending on the concentration of the solutions and determine whether the reaction is really feasible or not, and they can go for practical applications depending on the value we get. So the next one is the write the cell representation and calculate the EMF of a cell reaction. So here they have given zinc in the solid state. It means metal rod is dipped and the iron ions is having a molarity of 0.005 molar. So it is, they have given the molarity of that particular solution for the iron, and the zinc is a metal rod that is dipped in that particular cell. So this zinc rod is then oxidizing to Zn2 plus ions. So 2 plus ions are liberated and with a molarity of 0.01 molar, and iron is reducing to Fe as a deposition. So the given values for the electrodes. What are the given values for iron? For iron, it is minus 0.44 volt. See, if we see this, all the problems, the values are constant because they are constant for particular metal and as per the electrochemical series. So for iron, it is minus 0.44 volt and the zinc, it is plus 0.76 volt. So if we see this, in general in the electrochemical series, it is given like Zn2 plus gains 2 electrons and forms Zn. So it has a potential of minus 0.76 volt. And this iron also gains 2 electrons and form iron, and it is having a potential of minus 0.44 volt. But what is in the present case? It is converting from metal. This is the metal rod that is dipped. So this metal rod is oxidizing to Zn2 plus and 2 electrons are liberated. And iron is taking up these 2 electrons and forming iron that is in the solid state. So the net reaction will be, see here they have asked us to write cell representation. Whenever they are asking us to write cell representation, we have to write the net reaction. So these 2 electrons and these 2 electrons get cancelled and the right hand side and the left hand side of two reactions, and we get this net reaction, that is Zn in the solid plus Fe plus 2 ions will convert to Zn2 plus and Fe. So we have completed till here. So this is a cell representation. This is a cell representation. We have completed till cell representation. Now what we have to do? We have to calculate the EMF of that particular cell. So what do? We use the same formula like E cell is equal to E cathode minus E anode. So now we have to decide what is cathode and what is anode. So here oxidation is taking place, so anode, and here reduction is taking place, so cathode. So what is anode here? Zinc is anode and iron is cathode. So we have to substitute the values accordingly. So minus 0.44 of the iron is substituted here, minus of minus 0.76 is substituted here. So on addition we get plus 1.2 volt. As a higher value is having positive sign, the positive sign is given to this result. So this is again positive, the value is positive, so the reaction is feasible. Reaction is feasible. So the reaction will happen, feasible and spontaneous. Feasible and spontaneous. So this is how we calculate the cell EMF using the cell representation. Whenever they are asking cell representation, we have to give cell representation and then we will go for the EMF of that particular cell. So next one is write the net cell reaction of the following cell. So one cell is the magnesium. So the magnesium rod is dipped in magnesium sulfate or some magnesium ion solution. So that is having some molarity 0.02 molar magnesium salt. So some magnesium salt is used. Then what happens? Another cell is having silver ions. So silver nitrates or something. So 0.002 molar silver salt is dissolved. So that is Ag salt, and that is converting to Ag. Ag is depositing. So we should not really get confused here because of the molarities given. There is no question of taking consideration of these molarities whenever there are single electrode potentials given. So whenever the question is having single electrode potentials, the problem is having single electrode potentials, we need not worry about these molarities. So whatever can be the concentration of these salt solutions, we have to consider these single electrode potentials and use the calculations and find out the EMF. So now determine the EMF at 298 Kelvin. The examiner will be like confusing the student, giving these temperatures and molarities. So we have to just concentrate on like taking the consideration of single electrode potentials and going for the EMF. So the standard reduction potentials are given here. So for magnesium it is minus 2.37 and for silver it is plus 0.80 volt. So these are the electrode potentials that are given. So what's happening here? This is as per electrochemical series. As per electrochemical series, these are the single electrode potentials given. So magnesium 2 plus ions gains 2 electrons and forms magnesium, that is having an electrode potential of minus 2.37 volt. And the silver gaining 2 electrons forms silver and it is having plus 0.8 volt. So what is happening in the present case? The the present case is depicted only from the cell notation. So this is the cell notation. Still here it is called cell notation. This is a cell notation given. So Mg is converting to Mg2 plus. How does it happen? The Mg will convert to Mg2 plus, liberating 2 electrons. So oxidation is happening here. Increase in the oxidation state. So oxidation is happening. That will happen only at the anode. Anyway, there is an increase in oxidation state. It is oxidation is happening and it is called anode. And these 2 electrons are gained by silver and is forming Ag plus and 2 electrons are gained and forming silver. So here reduction is happening. How is it? Like plus 2 to 0 state. Anything in the metallic form is zero state and it is cathode. So the net reaction is like these two electrons and these two electrons get cancelled, and the Mg plus 2 silver 2 plus gives Mg2 plus and silver. So this is the net reaction. Now the cell net reaction is completed. Net cell reaction is completed. We have completed net cell reaction. Now it's like we have to calculate the EMF. For EMF, what is cathode here? It is plus 0.8. So plus 0.8 minus 2.37. On calculation we get 3.17. So this is the EMF for that particular cell. It is spontaneous reaction that will take place. Reaction is spontaneous and feasible because it is positive result we got. So the next one is calculate the EMF for the cell reaction at 25 degrees centigrade. See, if you see this question also, the question is has the temperature given here and the molarity of the solution. So concentration is given. Concentration of solutions is also given. So, and they have also given the single electrode potential for zinc minus 0.763, and for cadmium cell it is minus 0.403 volt. So they have also given this is the anode and this is the cathode. So it is very simple, like the zinc is anode and cadmium is cathode. How? Like zinc is increasing the oxidation state and oxidation is taking place and it is forming the anode, and for cadmium it is taking up electrons and reduction reaction is taking place and it forms cathode. In this way, we will write the net cell reaction cancelling the electrons that are present, because the electrons liberated from zinc electrode will be taken up by the cadmium electrode. So practically there will be cancellation of these two electrons. Therefore, we will be doing same thing in the reaction. Single half cell reactions also we will cancel them before writing the net reaction. So net reaction will be zinc plus cadmium 2 plus forms zinc 2 plus and cadmium deposited. So this is the net cell reaction. So from that we know what is anode and cathode. We have verified what the question is containing. So anode is zinc and cathode is cadmium electrode. So substitute the same thing like anode and cathode values and we get the value of plus 0.360 volt. So wherever there is a positive sign, it is again spontaneous reaction and the reaction is feasible. See, this is how we have to also verify the question that is containing. So there are given concentration where we haven't used in our calculation, but we should not get confused or carried away with these concentration and temperature values that are given in the question. So be very clear, like we have to go for the single electrode potentials. Whenever there is a mention of single electrode potentials, we have to use them straight away into the EMF formula and calculate the EMF of that particular cell. So the next one is, so these are the different cells, like we are taking the examples. So EMF of the cell reaction at 25 degrees centigrade and it is the magnesium and tin cells. So magnesium is one of the electrode and tin is forming the other electrode, other half cell. The half cell reactions are not given here in the question. So they have given cell notation. So this is a cell notation given. Magnesium is converting to Mg plus 2 and tin plus 2 is taking up these electrons and forming tin. So we will write the net reaction accordingly. So magnesium is converting to magnesium 2 plus oxidation is happening here and anode, and this is reduction. Taking up 2 electrons is reduction and cathode, forming cathode. So this is very simple, like again cancelling 2 electrons, we get magnesium plus tin 2 plus ions gives Mg2 plus and tin. So using the formula again, like in this we will be substituting cathode and anode values. So cathode minus 0.136 minus of minus 2 minus 2.34. So we will be substituting the values and we get 2.2 volt cell. The cell voltage of that particular EMF of that particular cell is plus 2.20 volt. So this is how we use, like even here they gave concentration, so need not worry about the concentrations because we already have single electrode potential values. Next is calculate the EMF for cell reaction at 25 degrees centigrade given nickel and copper electrodes. Nickel and copper cells. So one of the cell is nickel and the other cell is copper. So nickel is having minus 0.25 volt electrode potential and copper is having plus 0.34 volt. So they have given cell notation. This is the cell notation. Cell notation. As we have discussed in the previous slides, all the reactions, any problem will be containing a cell notation and electrode potentials if at all they are asking for the EMF of that particular cell. So what is given here, that nickel is converting to a nickel plus 2 ions. So nickel is converting to nickel plus 2 ions. So oxidation is happening. Oxidation, that is, it is the anode, and here reduction is happening. Reduction is happening and cathode. So again these two electrons will get cancelled and the nickel plus copper 2 plus ions forms nickel 2 plus and copper. This is the net reaction. Net reaction. So we have written the net reaction. Now we have decided what is anode and cathode. Now substitute into the formula. The cathode value is plus 0.34 plus 0.34 minus 0.25. So after calculating we get plus 0.59 volt. Again the reaction. So depending on the single electrode potentials and the tendency for accepting or releasing electrons, the EMF of that particular cell will depend. So depending on that, we apply in the practical applications, like how much voltage we require, we club two different electrodes and use it in the practical applications. Next is calculate the EMF for the cell reaction at 25 degrees centigrade for given cells, that is the electrodes. Two electrodes are given, like tin electrode is having minus 0.136 volt and lead is having minus 0.126. So they have given a reaction. Tin is converting to lead SN2 plus and lead 2 plus is converting to lead. So this is reduction is happening. So we will write a overall reaction. Tin is converting to tin 2 plus. Increase in the oxidation state. Increase in the oxidation state. Oxidation, anode. And there is a decrease in the oxidation state. So reduction. So cathode. This is how we have to verify. Again, cancelling these two electrons, we get tin plus lead 2 plus ions will convert to tin 2 plus and lead. Tin 2 plus and lead. This is the overall reaction. So again, the cathode minus anode, E cathode minus E anode. E cathode minus E anode. So substitute the voltage, the electrode potentials here, minus 0.126 volt, minus 0.136 volt. So we get 0.01 volt. So if we see this value, it is very less. It means this cell will produce very less EMF when compared to other combination of electrodes. So this is how we have to decide before combining any two electrodes forming a cell. But still it is spontaneous reaction that will take place, and the reaction will be feasible also. So next is the calculate the EMF for the cell reaction at 25 degrees centigrade again with zinc and silver electrodes. We are using zinc and silver electrode. So here this zinc is having minus 0.76 volt and silver is having minus 0.80 volt. So they have given the cell notation. Cell notation is given. So the zinc plate is dipped in zinc sulfate solution and the zinc is converting to zinc 2 plus ions. So this is what is happening here. Oxidation is happening here. So if we see this example, like for this problem, they have given Ag plus to Ag. So Ag plus to Ag, it is only having one. So here one electron is taking up and forming Ag. But balancing the reaction, for writing a net reaction, we have to multiply with 2. This reaction will be multiplied with 2 and we get 2 Ag, 2 electrons and 2 Ag. solid or the deposit. So this is again reduction and cathode. So whenever we multiply with 2, we get 2Ag plus 2 electrons, giving rise to 2Ag. This S represents solid state. It means depositing on the electrode. So the net reaction will be Zn plus 2Ag2 plus gives rise to Zn2 plus and 2Ag. So whenever there is in bracket in the subscript, if it is S, it is solid. If it is S, solid, L, liquid, and G is gas. So the state, we are depicting the state of that particular element. So the E cell or the EMF is calculated here. So cathode minus anode. So here what is a cathode here? It is the silver electrode is a cathode, minus 0.80 volt, minus of minus. This is zinc. This is zinc. This is silver. So substitute the values and we get plus 1.56 volt. So this is very good voltage that we are obtaining in this combination of electrodes. So this can be used in lot of applications. Next is the equilibrium constant of the reaction. This is the reaction silver plus iron giving rise to Ag plus and iron 2 plus is this. Equilibrium constant is K. They have given K. Find out the reduction or the standard electrode potential of iron 3 plus to iron 2 plus electrode. So this is for this electrode we have to find out the electrode potential, and if the standard reduction potential for the silver electrode is plus 0.799 volt. So they have given the standard electrode potential for silver electrode and EMF is also given. So here this is a typical question, like they have given EMF is given already. We are taking EMF, then equilibrium constant is given, and standard reduction potentials are given. For what? For silver electrode. For silver electrode, they give EMF reduction potential and equilibrium constant. So we will see how to deal with this. Like for the above reaction, the cell can be represented like Fe2 plus ion is converting to Fe3 plus ion. So there is an increase in oxidation state, and Ag plus is converting to Ag0. So there is a reduction. So this is anode and this is cathode. Silver is cathode. So substitute in the same way, like cathode, EMF is already given. Now what we have to find out here? Find out the electrode potential for iron. Iron we have to find out. So EMF is already given, is equal to 0.799 volt, and we have to find out this. So that is around after recalculation, it is plus 0.771 volt. So this is how there are different framing of questions. They will be giving lot of results, like a lot of data parameters for different parameters. But here we are not using, they have given the equilibrium constant, but still we are not using the equilibrium constant. Why? Because we only require the standard reduction potential for the electrode iron. So what we require for that? They have already given EMF. Whenever they have given EMF, the same formula E cell can be used, E cathode minus E anode. So whenever they are giving the main value, like EMF value is given, we will substitute obviously in the same equation. We need not go for the nearest equation. So in this way also there are some questions to be asked. So these cell EMF can be present, and they have already given for the silver electrode cathode. So cathode we will be substituting here for silver and we will be finding iron. So it is very simple. After reanalyzing, any problem can be reanalyzed properly, and the substitution of values will give the correct, accurate result. So this is how the reaction is again feasible and spontaneous. Whenever there is a negative value that we are obtaining, if at all there is negative value obtaining in the answer or the problem, it means that the reaction is not feasible. So the reaction is not feasible, it means it cannot react itself. we have to give some energy for the reaction to happen. It means non-spontaneous reaction, and the reaction is not feasible. So this is how we use the EMF for calculating the understanding the potential of that particular cell and giving for the further applications in the practical world. So for a voltaic cell, we generally use zinc and copper electrodes, like we will be calculating the EMF. So depending on the concentration also we will be using, but here we are using only EMF formula for calculating the EMF, wherein cathode and anode values are given. So all these problems, like wherever the single electrode potentials are given, we have to blindly go for this formula and use it. Just replace, like find out what is cathode and what is anode in that particular cell notation and substitute the values and get the result. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.